power. Miller, what is the equation for power?
The derivative of work as a function of time.
Derivative of work as a function of time. So, in this particular case, we're actually talking about the derivative of, rather than the work, the energy associated with it. So the derivative of the energy as a function of time. We know the energy is equal to the charge times the electric potential difference. The electric potential energy is equal to charge times the electric potential difference. We therefore have, if the electric potential difference, we have then power is equal to the derivative of charge as a function of time multiplied by the electric potential difference. What is dq dt? Mitch? Current. Power equals current times electric potential difference. We have this equation for electric potential difference equal to current times resistance. So we can substitute in here current times resistance for the electric potential difference. We therefore get power is equal to current squared times resistance. We can also substitute in, if we rearrange the equation to get current, and the current we can replace that with electric potential difference divided by resistance, which is squared multiplied by resistance. That's equal to then electric potential difference squared divided by resistance squared multiplied by resistance, or electric potential difference squared divided by resistance. One of our r's cancels out. So we get power is equal to current times electric potential difference. It is also equal to current squared times resistance, and it is also equal to the electric potential difference squared divided by the resistance. Three different equations for the power in a circuit. Just depends whether you have current, which of the two you have or are trying to find, current, resistance, and electric potential difference. So power is the rate at which energy is being converted to what? Let's take those as an example, the light bulbs. Those light bulbs right now have a certain rating, power rating. I don't know what it is, 60 watts, something like that. Watts, that's joules per second. This is the rate at which those light bulbs are converting electrical potential energy into Jenkins.
Light,
and
heat,
and
sound.
Light, heat, and sound. It's the rate at which they are converting electrical potential energy into light, heat, and sound. Example. In your house, you have outlets. There is an electric potential difference standardized across the United States for those outlets. The electric potential difference of the outlets of your house class are 120 watts. So, this is something you should know. The electric potential difference in a standard US household is 120 volts. So, let's take two light bulbs. Let's say we have a 100 watt and a 60 watt light bulb. And let's figure out the resistance of these two light bulbs. How are we going to figure out the resistance of one of these light bulbs? Bill?
Well, you have like P equal, or power equals current times the potential difference. And then
why is this not going to get us directly there? We could get there this way, but it's going to be roundabout. Emily?
We don't know the current.
We don't know the current. Jake?
There's no resistance in the equation.
There's no resistance to the equation. There you go. Two. Yeah, thanks. So we really should pick the power equation that has resistance in it and should have electric potential difference. So we should use power equals the electric potential difference squared divided by the resistance. In other words, resistance equals the electric potential difference squared divided by the power. We can go through and do this twice. We have the resistance for the 100 watt bulb then is going to be 120 squared divided by 100. And the resistance of the 60 watt light bulb is going to be 120 squared divided by 60. Please. 120 squared divided by 100, 144 ohms. Yes?
Yes.
And 120 squared divided by 60?
240.
240? So we have the resistances of these two. Just a basic problem going through figuring out resistances of light bulbs. Now, a fun game you can play at home. You can find any electrical appliance, and you can read the back of it. For example, this monitor is at 1.5 amps. So, this monitor draws 1.5 amps. In other words, 1.5 coulombs per second goes through that monitor. In general, I pay approximately 10 cents per kilowatt hour. I actually pay slightly more than that, but I'm assuming that the school district pays slightly less. But let's go with 10 cents per hour. We could figure out how much it costs the school district for me to have this monitor on. Let's say I have it on for about 8 hours a day. Zach, how do you want to start? We actually don't want to convert it into seconds, and the reason is because we pay in kilowatt hours, right? So hours is actually in what we pay, so we want to convert to seconds. Gary.
Yes.
Thoughts?
Not many thoughts.
Come on, give me something here. 1.5 amps.
Use an equation for amps for current.
Okay, what equation?
Not really sure.
Help them out. There's one given that is not listed here that you should know. Jenkins.
Delta V equals 1.
We know the electric potential difference, right? It's plugged into an outlet here in the United States, so the electric potential difference should be 120 volts. So that is a piece of information that is very useful. You could use this, Gary, to figure out.
Delta V equals IR.
We could use it to figure out the resistance of the monitor, but we don't need to. Meg?
We use this to find power.
We could use it to find the power, okay? The power is equal to, in terms of current and electric potential difference, it is I delta V, current times the electric potential difference. So 1.5 times the electric potential difference of 120 volts. So the power of my monitor is 180 watts. So my monitor is converting 180 joules of energy per second into heat, light, and sound, and moving electrons around, all sorts of stuff like that. Okay. What now? So let's convert this to kilowatts. So we know 1,000 watts of power is equal to 0.180 kilowatts. We now have the number of kilowatts. But we have yet to figure it out in kilowatt, bless you, hours. How do I figure out the number of kilowatt hours that this uses per day? Just multiply by 8 hours, right? Because we know 8 hours per day is what this is on for. So if I take our 0.180 kilowatts, multiply it by 8 hours, I will get kilowatt hours. We're close. We have figured out the number of kilowatt hours. We need to figure out how much it costs. Vlad?
Well, we're paying 10 cents per day.
No, 10 cents per kilowatt hour.
10 cents per kilowatt hour. So we're going to multiply that by 10 cents per kilowatt. 5 cents.
If we take our 1.44 kilowatt hours and multiply it by 10 cents per kilowatt hour, kilowatt hours cancel out, and we will get 14.4 cents. Is what the school district pays approximately per day for a single monitor. I'm not going to argue one way or the other, but I think you agree we probably have a couple monitors in the building. And you could probably agree that it's probably not in the best interest to leave the monitor on overnight. Right? Okay. Kilowatt hour. Let's take a look at this basic idea. Because we pay the power company in dollars per kilowatt hour. So what is a kilowatt hour? Let's break it down into something that actually makes sense. Kilowatt hours. Well, kilowatts, we know we can multiply by 1,000 watts and 1 kilowatt. We can cancel this out. We get 1,000 watt hours. 1,000 watt hours. What is a watt again, Dorstead? Joules per second. So it is 1,000 joule hours per second. So we have hours and seconds in here. So let's get rid of one or the other. So we have 1,000 joules per second. Let's get rid of hours so we can multiply by 1 hour on the bottom and 3,600 seconds on the top. Hours cancel out and seconds cancel out. And we get 3.6 times 10 to the 6th, what? Joules. 1 kilowatt hour. Kilowatt hour sounds like it has to do with power, correct? Does it have to do with power? Is it a unit of power? It is a unit of energy. Kilowatt hour sounds like something which it is not. Please understand, kilowatt hour is a unit of energy. Specifically, you can figure out that 1 kilowatt hour is 3.6 times 10 to the 6th joules.